All right, this is our SCUDEM project. We chose problem C, teaching Fritz to catch. I'm Michael Hoefler.
I'm Alexander Seamark.
And I'm Elizabeth Fetter. So this is an outline of the contents of our presentation, starting with the introduction that we just had, and then we're going to go over the variables and assumptions. We're going to go over a basic model for the dog catching the treat, and then we're going to go to two more complex models, and then finish up with some conclusions. And for each of our three models, we're going to go over advantages and disadvantages and why we move on to the next more complex iteration of that model. First, we have these variables and assumptions. So the main thing to note here is that for the dog, there's not really any obstacles, that the dog can actually run as fast as our model says it can, and that there's no air resistance. Variables right here, most important to note is that it's time in seconds since the treat was thrown, it's meters and meters per second for the velocity, and that your x of t, y of t, and z of t are the position of the treat after time t seconds in meters, and their x sub d of t and y sub d of t are the x and y positions of the dog in meters since at time t since the treat was thrown. First, we model the motion of the treat using parametric equations. So we have x of t, y of t, and z of t to model the 3D locations of the treat. For the x of t, it's the x position of the treat plus the v sub x of t, which is the x velocity of the treat. For the y position of the treat, we assumed that it was a constant c as we defined in our variables, and that's to just kind of simplify the model, and the treat's always going to be along that direction. And then lastly, for the z of t plane, it's the model for projectile motion, so negative 1/2 gt squared plus v sub y of t plus y of 0, and the g is negative 9.8 meters per squared, so the gravity constant. Then from that, we were able to gain this very basic model, which are these two differential equations for the x position of the dog and the y position of the dog in that plane. And they're both dependent on the vertical position of the treat, and the x position of the dog is also dependent on the x position of the treat, and the y position of the dog is dependent on the y position of the treat. And for each, we have these constants, which we can, the A, B, C, D constants, and we can determine those to ensure that the treat and the dog get to the same place at the same time, and the dog can actually catch the treat. So these are our solutions from the equations seen before, and when we pair this with the initial conditions that the dog is starting at the origin, and that also when the dog gets close enough to the treat in the x and y, kind of in the x and y direction, that it can actually catch the treat, and that's in epsilon. And so the advantages of this pretty simple model, which is the model is separable, so we can solve it by hand, and kind of the advantages of this is that, I mean, A, it's simple, so like I said, we can solve it by hand, and then when we vary those A, B, C, D constants to properly get the correct ball or treat and dog placement, we get a pretty accurate model of the dog catching the treat. On the flip side of that, the disadvantages are that when we don't get those good ABCD constants, the model doesn't really work. And so because of that, we explored more complex models to look at how the dog might be catching the treat.
To address some of the limitations of our basic model, we did some further research and found a couple more models. One of the models we found was the optical acceleration cancellation model, and this was created by a guy named Chapman in 1968 to look at how a catcher might catch the ball from a batter in baseball. So basically, this model looks at, there will be a parabola that follows the path of the ball, and then the catcher will move forward, and he'll be changing the angle at which he's sort of looking at the ball to maintain this constant optical velocity, which is key to catching the ball because if the item is changing acceleration, it's harder for the brain to calculate like where it's going to land, and thus if there's no acceleration, it's much easier and more accurate, which allows for a better catch or a more likely catch. So this model shows it. Here's a couple variables. We don't want to waste your time going over them, so we just listed them here. But basically, there's tangent of theta, which equals the opposite component of the angle, which is the y component, and then the adjacent, which is the r minus x. And there's also some of the s in there to account for the dog's movement, and this all gets you the tangent angle, elevation angle, which is the angle that the person is looking at the ball to maintain that constant optical velocity. And then the t minus over here just accounts for how the ball, when the dog is getting the ball from the owner, he's not going to immediately like recognize like which way the ball is going. He's going to have like a little bit of a delay. So that's to account for that. And then as we can see in this model, the tangent elevation angle needs to be exactly like in a straight line linear, so that the player's able to catch it, because if it's too high and it starts like curving up, then the player will not be able to catch it because they won't be in the right spot, or if it's too low, they also won't be able to catch it because they're not in the right spot, which is shown perfectly by Chapman's model of catching a baseball. And then the elevation angle theta of the treat is at is seen by the dog standing at distance s from where the treat comes down, and distance r from the origin. This is just to show that like the tangent of theta, the output from tangent theta for the elevation angle needs to be a constant, so that the dog will be able to catch the treat when he eventually comes down. So we tried to model this on our own. We created a parabola, a square root, and a linear graph. On the linear line, you can see that the treat is caught because the tangent of elevation angle increases at a linear rate. But on the square root one, it doesn't increase at a linear rate, so it increases at a much slower rate. So Fritz undercompensates for the change in the position of the ball, and then the parabola, the elevation angle changes at a much greater rate, causing him to overcompensate for the position of the ball.
All right, so the previous OAC model covered by Cadet Seamark has proven to be pretty accurate, but there's a couple issues that it's faced. One of those is it's had some criticism about our ability to perceive whether acceleration is present or not. It's been said that we're not really necessarily able to perceive like small differences in acceleration, whether it's happening or not. And there since has been a different like model proposed for catching baseballs. So this is another baseball-centered model, but it's also going to be applicable for the dog catching the treat, which is what we're covering for this project. So this is called the LOT model. It stands for linear optical trajectory, and basically the model assumes that the dog is going to run to keep the apparent trajectory of the toy linear, so it appears to move in a constant direction relative to the horizontal. So that's a little bit confusing, but another way to say that is basically that this angle is going to stay the same as the dog is approaching the treat. So what we're going to end up with here is a whole bunch of similar triangles, and this angle here that's staying the same, we're going to call that gamma. So keeping this figure in mind, if we take tangent of gamma, that's going to be basically the y over the x. So this is the y of the ball. This is the x of the ball minus the x of the dog. So as the dog moves along, that triangle is going to get smaller, as you saw in the previous figure. And if we solve for x of d, the x position of the dog, we get this model right here for basically the dog running. Yeah, so this is another perspective of the LOT model where it's actually in full 3D, and the dog or the player is in a different plane as the ball. Whenever we modeled this, we're going to keep it sort of in 2 dimensions, but this is just to show how things would get a little bit more complicated if that 3rd dimension was present and the dog was like not centered with the treat. You actually have 2 angles that you have to consider, and things get a little bit more complicated. All right, so this is going to be a little model that we created based on that linear optical trajectory idea that we covered in the previous few slides. It's a little bit simple because we're still considering the kind of the 2D version of this, even though this is being shown in the 3D plane. But what you're going to see is, if I play this, the dog in blue is going to speed up as it approaches the treat. The treat's kind of starting up, up here and dropping down. It's going to speed up and catch that treat, which is pretty accurate to how you might see a dog kind of hesitate as the treat is higher in the air, but then really pick up the pace as it closes in and catches that treat.
Now we will discuss some conclusions that we learned from making this model. First, we learned that there are a lot of complex patterns that we need to recognize, humans and dogs in this scenario need to recognize in order to be able to catch something in midair. So from this, we kind of learned that Fritz isn't necessarily clumsy. It's just a very hard process to learn how to catch something because the brain has to recognize so many patterns with the velocity and the angles of the projectile. So in order to make it easier for Fritz, or to help Fritz learn how to catch, he should practice more so his brain can learn these patterns and he can more accurately catch the projectile motion or the treat. And if the owner wants to make it harder for Fritz and make more money from these videos, the owner could throw it at an oblique angle or put some spin on it so that Fritz can't recognize those patterns and will continue to be unable to catch the treat. Thank you very much. These are our works cited. Thank you.